Hi, I'm Sebastian, and as the CEO of Global Consulting Company, I'm very glad that our team has been selected to assess the road network of the University of Birmingham. With our experience and knowledge, we are going to build the best option to satisfy the requirement of our client.
Hi, I'm Matthew.
My name is Ika. We are in Communication Department of Global Consulting Company.
Our goals are to develop, conceptualize and execute the production of projects through mass multimedia.
We also ensure our product meets our clients' needs.
Hi, I'm Tom.
I'm Abbas.
I'm Tim.
And we're the pavement engineers for the company. We're in charge of assessing defects, developing the software, identifying intervention levels and determining cost for the pavement management system's results.
Hi, my name is August.
Hi, my name is Bala. We are in charge of functional part of Global Consulting Company.
And our work is to plan and organize the field.
Hi, I'm Emmanuel, and we are part of the Health, Safety and Environment Department.
Our team ensures the personal safety of all engineers by providing safety equipment and also managing traffic on site.
The University of Birmingham was the UK's first civic or red brick university, established in 1900. The university is renowned for many subjects and was crowned University of the Year 2014 and is ranked 118th in the world. It is a public research university located in Edgbaston, Birmingham, United Kingdom, 3 miles southwest of Birmingham city centre. The road network along the 25-acre site consists of University Road West, Westgate, Southwest Campus, Terrace Road, Grange Gate, Ring Road North and Ring Road South. The aim of our project is to assess the maintenance needs of the university's Edgbaston campus road network through a pavement management system. Asset management is a systematic process for maintaining, upgrading and operating physical assets cost effectively. A pavement management system is the systematic process of maintaining, upgrading and operating pavement assets cost effectively. The aim of a pavement management system is to operate, maintain and restore the road network to meet performance requirements, but also to provide decision makers with the necessary tools for efficient and sustainable management of the whole road network. The benefits of maintaining the road network in good condition are to improve safety and user comfort, to reduce both road user and life cycle costs. The objectives of our project are to establish a referencing system for the campus to enable the undertaking of a condition assessment, to identify typical treatments and to define intervention levels based upon treatment selection, and to prioritise treatments to attain optimum life cycle performance.
After defining the project's objectives and decision strategy, we created a referencing system to attribute data. Data collection was duly conducted and recorded in a database by 2 teams, focusing on international roughness and pavement condition index respectively. Software was created to analyse and determine both local and generic treatment requirements based upon both the international roughness and pavement condition indexes attributed to the current road condition. Each subsection's treatment needs were subsequently prioritised based upon both traffic levels and relative cost of the treatment to determine the most effective solution of maintaining the road network. Finally, we provide our conclusions and recommendations to our client. An initial site visit is a key step in the process of road assessment. It was carried out to define the requirements of a pavement management system for the university road network. The assessment enabled the company to attain an overall perception of the network condition, including the identification of major defects, section and subsection extents. It consists of a review of the whole network to be assessed. It helps to identify the major defects to get a first evaluation of the road condition. According to this first evaluation, we could find the road condition parameters to be collected among defects, roughness, traffic and skid resistance. We could then also divide optimally the campus network. As such, it was decided that functional evaluation would focus on roughness rather than skid resistance, given that the determination of a carriageway's skid resistance would be unimportant in determining surface treatment, in comparison to the International Roughness Index, given a low speed limit of 50 miles per hour. Pavement Condition Index is further used for the purposes of structural evaluation. These steps were essential to define our data collection strategy. Referencing involves breaking the network down into smaller sections, each of which can be defined neatly. The process of referencing implicates logical and physical activities. Each section should have homogeneous characteristics in terms of road class, traffic level, road geometry, and type of pavement, and needs to be identified with an appropriate reference. Based on this, the road networking analysis was divided into 7 sections, each of which was divided into subsections for more detailed pavement condition analysis. The road length selected for maintenance follows mainly the approach of short, fixed subsections, but in some cases, dynamic subsectioning was used due to a different type of pavement existing in the network, and to fulfill the total length of a section. Regarding the inventory, the information collected was based on a basic road inventory approach, which included the geometry, length, pavement material, and road gradient as a continuous item inventory, and gully pots drainage as a point item inventory.
To determine the performance of a pavement in terms of serviceability and structural capacity, it is necessary to evaluate its condition. There are 2 types of evaluation: functional and structural evaluation. Functional evaluation provides information about surface characteristics that directly affect user safety and comfort. The main characteristics surveyed are skid resistance, surface texture, and roughness. Structural evaluation provides information on pavement performance under traffic loading and environmental conditions. Survey characteristics are related to structural performance, pavement distress, and mechanical properties. In this project, we focus on roughness and on pavement distress in terms of cracking and surface defects. Our collected data consists of roughness, pavement distress, traffic levels, and visual pavement condition. Several devices such as Merlin, Walking Profiler, or Dynatest Multifunctional are available to collect roughness data. We chose the Merlin because it is a low cost and simple machine that meets the data requirements. Pavement roughness is a main parameter of road condition assessment which directly influences road user costs. It is characterised by the International Roughness Index. Before the Merlin can be used, it requires 2 steps of calibration. First, the position of the probe has to be vertically and laterally adjusted so that it is correctly aligned with the front and rear feet. For the lateral alignment, it is correctly calibrated when the string is in the middle of the probe while the string is stretched between the tyre and the rear foot. For the vertical alignment, it is properly adjusted when the string touches the probe while the pointer is at the centre of the chart. The second step calibrates the measurements based upon the deviation of a known defect depth. The Merlin is rested with the probe on a smooth surface and the position of the pointer on the chart is carefully marked. The probe is raised and a metal calibration block of known dimension is placed under the probe and the new position of the pointer is marked. The process should be repeated to check that the values are consistent. The measurements made on the chart should then be multiplied by this scaling factor. Data collection through the use of Merlin was conducted for 200 measurements within each section to obtain a sufficiently large number of data points to determine the subsection's International Roughness Index. For every wheel revolution, our technician marked the position of the pointer on the chart. During the measurements, we were very exposed to potential collisions with the cars. In order to remedy this problem, each group designated a safety officer in order to reduce this risk.
detailed visual inspection is required within each individual subsection to identify and classify defects in accordance with ASTM. In turn, this data is analysed and weighted to determine the unbiased pavement condition index of each subsection to allow the identification of appropriate generic or localised treatments. Given the relatively small length and varied condition of the university road network, it was decided that detailed visual inspection should be carried out along the entire length of the network, in preference for undertaking random sampling, which would not account for localised defects.
We use the measuring wheel to collect the length of sections, the width of the carriageway, the area of cracking and the size of defects. We also used a ruler to collect the depth and width of potholes.
The detailed visual inspection categorises both surface defects and cracking into a number of subcategories consisting of alligator cracking, block cracking, longitudinal and transverse cracking, patching, potholes. A further category of ironwork defects was also added based upon the initial site inspection, with deduct values considered to be represented by potholes. Individual defects are measured based upon the length, width, or in the case of potholes, the whole number of ½ metre squared defects at each specific location. Measurement is carried out by a surveyor's wheel to determine defects to the nearest 0.1 metre for purposes of repeatability and speed, whilst not unduly affecting accuracy. Degradation and hence treatment requirements should consider road user numbers for each subsection to prioritise maintenance. Road user numbers were determined for each subsection based upon a peak 30-minute traffic survey covering all vehicle types. These vehicle numbers were converted to equivalent passenger cars to gauge overall road hierarchy. A more extensive survey was not necessary for this analysis, as the first degree decision system considers current defect treatment rather than whole life treatments.
Data collected for roughness is used to calculate RRI. Pavement distress data is used for the calculation of PCI. Traffic data is analysed to obtain subsection hierarchy. A factor D, together with 200 measurements, are used to determine the RRI for the section based upon the RRI roughness equation. Individual defects are recorded within a generic subsection database as a defect type, severity and a unit of measure. As such, each defect is assigned a surface area to allow the determination of the total percentage of each defect within a 20 metre subsection increment and hence the overall subsection. The overall subsection percentage per defect type and severity level, as calculated from field measurements, is duly assigned a deduct value to correct for the differing impacts upon the road user's driving experience in regard to defect type and severity level. The deduct values are thence corrected to a maximum corrected deduct value through the use of the ASTM procedure, which lists the deduct values in descending order before determining the number of allowable deduct values and applying the correction curve for asphalt pavements. Pavement condition index is hence determined as the result of 100 minus the maximum corrected deduct value.
Defects on the pavements were categorised into cracking and other surface defects, with alligator, block, longitudinal and transverse cracking being identified, in addition to patching, potholes, ironwork and ravelling. Generic treatment is based upon the IRI and PCI index results. IRI is categorised into good, moderate and poor conditions, with poor conditions requiring resurfacing, whilst PCI is categorised into fail, poor, moderate and good conditions, with fail requiring reconstruction and poor resurfacing. The required generic treatment is the maximum of either result. However, each generic treatment requires consideration of individual defect severity, whose treatment may exceed the PCI or IRI index requirements to ensure all defects are treated. If defects do not exist, the highest level generic treatment result is required, which may be reconstruction, resurface, or do nothing. However, if defects exist, then treatment is based upon individual defects and defect severity levels, with typical treatment for a low or medium severity defect being a simple fill, seal or patch repair, whilst high-level defects require more expensive, complex treatment such as road resurfacing or full-depth reconstruction. Currently, local road asset management systems therefore generally only undertake repair on high-severity defects where road safety is impaired due to budget constraints.
The highest level generic treatment is selected based upon both the RRI and PCI results. If the chosen treatment is considered defect severity, then localised treatment is selected. For instance, for the subsection RRS 03001, it is recommended to consider the defect severity. For this subsection, it is seen that treatments such as seal and patching in specific areas are suggested. PCI and RRI intervention levels can be adjusted within the software to meet changing performance requirements. In this case, the upper RRI threshold for considered defect severity is lowered from 4 to 2, resulting in the reclassification of many sections. In turn, cost and prioritisation is affected. The types of deterioration observed on the University of Birmingham Edgbaston road network can be attributed to increased equivalent traffic levels associated with construction works and increased student and staff numbers, together with an ageing pavement subject to environmental effects. Defects including potholes, block and longitudinal cracking are attributed to environmental related factors such as extreme temperatures including hot or cold weather and freeze thawing, together with increased rainfall levels. However, the high road network age and high levels of utility cut patching are also key causes of potholes throughout the network and particularly adjacent to damaged patching. Increased traffic loading on the pavement structure is likely to have caused the high levels of alligator cracking and localised ravelling due to failure of both the surface layer and base course or subgrade, which were not designed for such heavy loading requirements. Other factors include overall surface wear resulting from an ageing pavement structure. However, recently resurfaced subsections also display signs of distress due to poor workmanship at joint details and excessive patching, which has decreased the life of the network. Further areas which are in relatively good condition have RRI levels which could be considered to require maintenance treatment to improve riding quality due to poor road geometry. However, given the low speed within the network, such treatment may not be deemed necessary and hence pavement distress has been weighted more strongly.
Prioritisation is based upon traffic levels within each subsection, together with the relative costs associated with each treatment. Each treatment within each subsection is hence assigned a priority to optimise resource use. Traffic prioritisation was determined based upon the number of equivalent passenger car units accessing a subsection during 30 minutes of heat usage, whilst treatment prioritisation was determined as a simple hierarchy. This method therefore accounts for maintenance activities and traffic levels in terms of their impact on road degradation and preservation.
Treatment ranking is based upon the type of treatment intervention, where 0 corresponds to no treatment and 7 to reconstruction. Traffic ranking is based upon the number of vehicles in terms of equivalent passenger car units, where 4 corresponds to the range of the lower traffic volume and 1 to the range of the highest traffic volume. Prioritisation is calculated based both upon traffic and treatment ranking, as seen in this matrix. Our system reviewed road defects and roughness upon the campus network from a general and specific perspective to determine the subsection condition of the road network based upon defect types, severities and serviceability through known numerical models. Treatment costs per subsection vary depending upon defect severity and localised treatment requirements, which gives the client the flexibility to determine intervention levels and hence treatments in regards to the available budget. From a life cycle point of view, we recommend the delayed resurfacing or reconstruction upon construction routes until current works are completed to reduce surface wear upon the treated road due to high levels of construction traffic. However, treatments and subsections upon non-construction routes should be completed as per the recommended prioritisation. Localised patching and specific treatments should be conducted upon those subsections that are not generically treated to ensure road user safety. The total cost to provide adequate performance across the whole network over the next 5 years and beyond is £238,000.
And to conclude, here you can see our finalised prioritisation ranking for each subsection.